Video contain 1. Introduction to machine learning. 2. Introduction to SVM. 3. Balanced and imbalanced data. 4. Controlling bias with asymmetric SVM. 5. Methodology of asymmetric SVM. 6. Results and observations. 7. Advantages of asymmetric SVM. Machine learning can be divided into supervised learning, which includes classification and regression, and unsupervised learning, which involves clustering. Supervised learning uses labeled data to train models, like teaching a system to recognize apples and strawberries. Unsupervised learning finds patterns in unlabeled data, like grouping garlic, spicy, and aubergine without predefined labels. We are using the SVM classification technique to train the model. SVM Support Vector Machine. Support Vector Machine SVM is a powerful supervised machine learning algorithm used for both classification and regression tasks, although it is mostly used for classification. When using SVM for classification with imbalanced datasets, the model may bias towards the majority class. To optimize this, Asymmetric SVM adjusts the margin by assigning different penalties to misclassifications of minority and majority classes, improving the model's performance on imbalanced data. Methodology of SVM. We aim to minimize this equation. First part, the norm of the weight vector divided by 2, controls the model's simplicity. Smaller weights mean a simpler, more general model. Next, we have two penalty terms, one for the positive class and one for the negative class. C+ represents the penalty for misclassified positive class samples, C- is for negative class samples. This allows us to treat the two classes differently, especially when they are imbalanced.
Constraint for the positive class blue text. If a sample belongs to the positive class, or y sub I equals 1, the equation ensures that the sample lies on the correct side of the margin boundary. The slack variable xi plus allows some misclassification, but it must always be non-negative, meaning the classifier must try its best to correctly classify the positive samples. Constraint for the negative class red text. Similarly, if a sample belongs to the negative class, or y sub I equals -1, this equation makes sure that the sample lies on the correct side of the margin for the negative class. Again, the slack variable xi minus allows for some misclassification, but it has to be non-negative, ensuring that the classifier handles the negative samples properly. Total number of training patterns equals 400. This means the model is trained using 400 examples, or data points. Number of positive patterns equals 217. Out of those 400 data points, 217 belong to the positive class.
Number of negative patterns equals 183. 183 of the 400 data points belong to the negative class, establishing the ratio between C+ and C-. This equation shows that we set the ratio of C+ and C-, the penalties for the positive and negative classes, in proportion to the number of negative and positive patterns. This helps the model account for the imbalance between the two classes by giving more importance to the class with fewer samples. The ratio between C+ and C- is established based on the number of negative patterns divided by the number of positive patterns. This ensures that the model adjusts for the class imbalance, and this ratio is assigned the value of lambda, a new parameter. In this equation, the same ratio, C+ over C-, is simplified to lambda. Lambda represents how much more weight the penalty for positive samples should carry compared to the negative samples. Finally, we rearrange the equation to express C+ in terms of lambda and C-. C+ is now equal to lambda times C-. This shows that the penalty for misclassifying positive samples is scaled based on lambda and the penalty for negative samples. In this analysis, we tested 20 different lambda values ranging from 0.12 to 0.0 to find the best performance for the asymmetric SVM. As we observe in the first graph, the false positive rate, false negative rate, and total error rate vary with different values of lambda. The second graph shows how the decision boundary areas also change as lambda increases. At around lambda values 1.2 to 1.4, we reach an optimal balance. The third plot visualizes the model's decision boundaries, confirming that this range provides the best results. So, the lambda values between 1.2 and 1.4 yield the most optimal output. Asymmetric SVM excels at managing imbalanced data, allowing sensitivity customization for specific classes. It improves model performance, reduces overfitting by focusing on the minority class, and is adaptable for real-world applications. Don't forget to hit the subscribe button and turn on the bell icon to stay updated with all our latest content. Thanks for watching.